previous lecture, we talked about the orbits and what they do, what they are, um, and they're not the orbits that you guys usually talk about in orbital mechanics or in rocketry, but rather group action, or it's a nickname for what is called a group action, which is a mapping between two groups. So, in today's video, we're going to be talking about measure. And what is measure? Well, I talked about measure in my in the first course that I taught, which is from biology, and in that course there was a lecture, which is surrounding mu bar, which is a measure for homosexual tendency, and this is usually around. This is split up into four parts, which is 0%, or it's measured in percentages, which is, or actually, it's the outcome first, or what it is first. So it's a function. So it's null for 0%, stable for 50%, and full, I think, or yeah, full or complete for 100%. And what mu bar basically does is assign a sort of label for your given for a person which has this percentage of homosexuality. And today we're going to be talking about sort of the what exactly mu bar is. What exactly is a measure? Now, if you guys haven't tried it by now, I highly suggest you guys watch the original video on what mu bar is and assigning measure for homosexual tendencies. And that's measured in percentages or in decimal form. But today we're just going to be talking about measure itself. So, what a measure is a function that assigns a value for a set. So, suppose we have a set A, and then we have a number line, probably the integers. Let's say integers. So this is 0, and then this goes off to infinity n, or actually real numbers. It's called R, the real numbers. And this is our set A. What a measure does, let's call the measure alpha. What alpha does is take an input, or any input, and then assigns this input to a certain integer or a certain number, excuse me, onto this part here. So what alpha does is assign a measure for each element in this set. So when we have a set here or an element here, put it through alpha and we get a number from this number line. That's what a measure is. And it's a generalization of the notion of mass, volume, surface area, stuff like that. Because we measure mass, volume, or surface area via numbers. We represent them via numbers on the real number line. So let's say we have a cube that has a surface area of let's say it has a surface area of 30 meters. And so that's the measure. 30 meters is the measure of that object or that cube, because we have the values of the cube, or we have rather the things we need to find the surface area. So we have a cube. We know that the surface area is basically just 6s squared, where s is the here. This is s squared, and then just multiply that by 6 because we have 6 sides. So our measure is 6s squared, or measure for the surface area. So it takes the input, which is the length of one of these lines that forms the cube, and then it spits out a number, or the measure of what the surface area is. So for any value s here, it assigns a value to each of these s. So not only do we have the measure of the surface area, but we can also have the measure of the volume, which is S cube, which is this length times width, length times width times height. So it's S cube. So that's the measure for the volume. So this time, instead of assigning S or every S or any possible length or edge of a cube that we know to be the surface area, this time we're assigning S to the volume of the cube. So there are many ways you can use measure, and there are many parts or topics concerning measure. But the most basic concept, or is what I said a while ago, that the measure assigns a value from a set. It assigns a set or assigns an element from a set to one of these. It corresponds one of these elements to a number, to a respective number on this real axis. And that's basically the concept of a measure. And as I said in the previous video, or in that video, we have an input space and an output space, which is two-dimensional. But it can actually just be one-dimensional. So this is our input space. This is our input space. So it's sort of fly. Here's our input space, and I'll call it H for measure of homosexuality. Alright, this is our input space, and then we have 0, I'm just gonna go, it ranges from 0 to 1. Right, so this is 0, this is 1/2, which is 50%, and this is 1. So this is our stuff, and then it can range from 0 to 100 in percentage, rather. We just express it as decimals. This is the same as 0, 50%, 100%. Alright, so what mu bar does, it takes any value here. So let's say we have, let's say 1/2. It takes 1/2, and then it sort of tells us, assigns what the label is, right? It tells us the label of the person. So let's say null, stable, and full. So this time mu bar assigns this onto stable, and 1/2, and then 1 is put through mu, and mu gives us full homosexual, and 0 gives us null, or a straight guy. So basically it's a measure. That's why I called it measures of homosexual tendencies, because we're measuring the percentage of how gay the person is, right? So mu bar basically assigns or gives us a measure of how gay the person is, and it can be applied in the opposite manner actually. And actually, that's the most logical or most intuitive way to explain mu bar. I didn't really explain it in a very intuitive way in the video where I actually discussed mu bar, but it's actually much better if we have the states null, stable, and full, and then we assign these states to a probability or a percentage. So 0, 1/2, 1. So this time, instead of actually assigning the percentage to each state, this time we're going to assign a given state to its corresponding percentage. So full is mapped by mu bar onto 1, stable is mapped by mu bar to 1/2, and null is mapped by mu bar to 0. And there's an intuitive way to sort of demonstrate these mappings, and that is through a mapping diagram. So I'll write the stuff again: null, stable, and full. 0, 1/2, 1. And so null is mapped onto 0 by mu bar, stable is mapped to 1/2 by mu bar, and full is mapped to 1 by mu bar. This is a straight bijective function. So yeah, and we can flip reverse and sort of take the inverse mu bar to map 0 onto null. So mu bar to the minus 1. And a 1/2 to stable by mu bar to the minus 1, and 1 onto full by a mu bar to the minus 1. So it maps it. And just so you know, map is just the same as function. We're moving null or corresponding null to 0. We're corresponding the stable homosexual to 1/2. We are corresponding the full homosexual to 1 or 100%. Percentages, this is 0%, this is 50%, and this is 100%. And in the inverse case, we're corresponding 0% to the null, 50% to the stable, and 100% to the full. And so that's the basic notion of what a measure is. It's a generalization, rather, of what we use to describe spatial things. So a measure is basically just a generalized notion of mass, volume, surface area, maybe even Dane invariant. A Dane invariant can be also called a measure. And even amount, even a certain amount of objects can be called a measure of how many things there are, right? So if I have two pencils with me, or if I have a scissor and a pencil with me, the measure of how many things I have right now in my hands is 2. And so likewise, if I add an eraser in here, the amount of things that are in my hand, or the measure of how many things are on my hand, on my left hand right now, is 3. And so on and so forth. So that's basically it for the measure, and it's a relatively straightforward concept.